Hey folks, today we're going to go ahead and get started by solving this problem. Now, this problem is going to look at centripetal forces, and more specifically, the kinds of things that act as centripetal forces and what they look like. So without further ado, let's get started. In the rotor ride to the right, the boy upside down, let's go ahead and circle that boy right here, has a mass of 55 kilograms. And as I'm going through, I'm going to go ahead and just highlight all of my givens. So we've got our 55 kilograms. The boy is 10 meters from the center of the circle, and his tangential speed is 17 meters per second. We're going to determine the magnitude and direction of each force acting on him. And so to do that, I'm going to start by drawing my free body diagram. Now, in case you don't remember, a free body diagram is just a picture that shows all of the forces acting on an object. And I'm going to go ahead and I'm going to represent my boy as a dot. Because remember, the quality of your picture does not matter. And in fact, it's actually a lot easier to draw a free body diagram if you aren't worried about what the physical situation looks like. So now I'm going to go ahead and I'm going to draw my forces. Now, our boy has mass and is on Earth, has gravity. So we know that gravity is acting on him, and gravity, as always, is going to be acting down. We also know that our boy is not falling down or flying up, so that means that there must be a force that is opposing gravity, that's equal and acting in the opposite direction, and that force in this situation is going to be friction, because if you look at the boy, the force that is going to be the force that would be holding him up against gravity is going to be parallel to the surface that he's on, and is resisting any change in motion. And so we know that the name of that force is friction. So let's go ahead and draw that up, the force of friction. And then finally, there needs to be a force that's acting in the radial direction, acting towards the center of the circle. And that force is coming straight out from our surface. It's perpendicular to our surface, and any force perpendicular to a surface acting out, resisting something going through that surface, is going to be the normal force. So I'm going to go ahead and draw that in as well. Now, some of you may be looking at this and feel a little confused because you're used to seeing free body diagrams where all of the forces are balanced. However, in this situation, we do not have a constant velocity. V does not equal constant. Because remember, the direction of the boy's motion is constantly changing, and we actually have a centripetal acceleration. Excuse me, I'm going to fix this. I'm going to say our centripetal acceleration is not equal to 0 because the direction is changing. If we did have a balanced force, the boy would just be moving in a straight line. He would not be traveling in a circle. And so this unbalanced force here is totally fine. It's actually exactly what we're looking for. So I'm going to go ahead and erase this. We don't really need this. And let's go ahead and start solving for our forces. I'm going to start with gravity because that's the easiest one to solve for. We know that gravity, the force of gravity, is given by the equation mg. And we know that our boy has a mass of 55 kilograms, and I'm going to assume we're on Earth because I've never seen one of these carnival rides anywhere else on any other planet. So we're going to assume g equals 9.8 meters per second squared down. So let's go ahead and stick that in our equation. We have our mass of 55 kilograms times g, 9.8 meters per second squared. And we can go ahead and multiply that out, and we get the force of gravity is equal to 540 newtons down. And now we are one force down and two more to solve. We have the magnitude here, and we have the direction here. So let's go ahead to our next force, and I am going to move on to friction, because I know that the magnitude of my friction force, which I'm going to represent by an absolute value sign, is equal to the magnitude of my gravitational force. And I know this because friction and gravity are pointing in opposite directions, and I know that the boy isn't falling or flying. He's not accelerating in that vertical direction, so our forces have to balance out. And so, nice and easy, I can say the force of friction is equal to 540 newtons up. So again, equal magnitude to gravity and opposite direction. Okay, now I'm ready. So this has all been review so far. You guys should have been used to seeing these things. What is going to be completely new is our normal force here, because this is going to be where we introduce centripetal forces. Now, the normal force, as I mentioned earlier, is acting as a centripetal force. Now, folks, I do want to say, this is very, very important. I do not want to see your centripetal force, F sub c, should not be in a free body diagram. And the reason for this is that your centripetal force is not a real force. Your centripetal force is a kind of general category, a general name for any force that acts to keep something moving in a circle. But the actual force doing that can change. So in our situation, it's a normal force. With the mass on the string that's being swung around in a circle, it's that tension in the string. And so I don't want you to write the centripetal force. I want you to write the force that is acting as the centripetal force. So here it's our normal force, which we can find by using our centripetal force equation. So we know that the force required to keep a boy with a mass of 55 kilograms traveling at a speed of 17 meters per second in a circle of a radius of 10 meters is given by mv squared over r, and that's going to be our mass here times our centripetal acceleration. So let's go ahead and stick in numbers. He has a mass of 55 kilograms. He's traveling at a tangential speed of 17 meters per second, and we're going to square all of that and divide by our radius of 10 meters. And that is going to give us a normal force of 2,000 newtons with a direction pointed to the center of the machine, so to the center. And there you have it, folks. You have successfully solved through one centripetal force problem. So now it's your turn. Go ahead, give it a shot, and see if you can solve some problems on your own.